Okay, so this is part 2 where I wanted to come back to this question 7, when is the object speeding up and slowing down? It took some time to talk about, you have to look at what the signs of both the velocity and acceleration are in order to tell whether it's accelerating or speeding up or decelerating or slowing down. So I wanted to make sure we understood what was going on here. So a lot of what we need is on the other page. So here are my 2 equations. And if you're asked to find where the object was speeding up or slowing down, the first thing you want to do is do a sign chart for velocity, which we already have. So we set velocity equal to 0, and on the other page we got time was at 2 seconds or -1 second. All right, and then we drew a number line. All right, so we did that first. We're going to do it again. And then you also need to find the critical points for acceleration. So you set acceleration equal to 0, and we got t equals 1/2 second. So that was from the other side. All right, you could do the work there if you want to. All right, now to answer this question, you need to be able to look at the signs of both velocity and acceleration. So what you want to do now is you want to create a number line with both of these things on there. So first of all, 0 seconds is all we need to worry about. Okay, and then 2 seconds and 1/2 second I'm going to put here. So here's 1/2 second, and here is 2 seconds. And these are critical points. And here I'm going to put the velocity results, sign analysis results, and I'm going to do the acceleration sign analysis results. So you do that, and you've got this and this. Okay, so we've created all these regions. Now, from the other page, we already figured out that this velocity function is a parabola, and so it's a plus. Here, if we put this -1 in here, it's positive until you get to -1, and then it's negative from -1 to 2. So that I'm going to put a negative right here and a negative right here, and then after 2, it's positive. Okay, so I kind of ignore this line because that is talking about acceleration. All right, and then from the other page, we found out that, basically what we're doing is we're saying for acceleration, where is 12t minus 6 greater than 0, and where is 12t minus 6 less than 0? And that it equals 0 at 2. So if you pick a number, it equals 0 at 1/2. So if you pick a number smaller than 1/2, like 1/4, you can see that's going to be negative. And if you pick a number bigger than 1/2, like 1, you can see that's going to be 6 is greater than 0. So that's positive. And then it's going to be positive. Okay, so see now you have a sign chart where you can tell where the signs of both velocity and acceleration are. All right, so the object is speeding up when the signs are the same. All right, so the signs are the same in 2 places, right here and right here. So the object is speeding up or accelerating on the interval from 0 to 1/2 and from 2 to infinity. And the object is slowing down or decelerating from 1/2 seconds to 2 seconds. All right, so that's how you would figure out the signs of velocity and acceleration to see whether it's accelerating or decelerating. Okay, now that rectilinear motion, straight line motion is a really important concept. So we're going to come back to it, but I do want to do a couple more examples and to show you how we can apply this rate of change to different sciences. And I highly recommend that you read the book section 3.7 because it gives you a whole lot more examples. But I'm just going to just do a couple more so we can get used to how to figure out all these letters, if there's different letters. So it says the magnitude F of the force exerted by Earth on an object is inversely proportional to the square of the distance r from that body to the center of the Earth. Okay, so what we have is an inverse proportion, so you have to go remember what that is. Now, the way I remember an inverse proportion is the two items, x and y. If they're inversely proportioned, that means when you multiply them together, it's going to equal some constant k. That's an inverse proportion. And it's an inverse proportion because when this x, like let's say it was x times y equals 12. I'm going to erase that. But when x is 6, y is 2. When x is, let's try it again. When x is 1, y is 12. When x is 2, y is 6. When x gets bigger, at 3, y goes down to 4. When x gets bigger, 6, y goes down to 2. So the inverse proportion is basically saying when one goes up, the other has to go down in order for them to multiply some constant k. Okay, so that's inverse proportion. And just to complete the thought, whenever I read something and it's a direct proportion, I think of this. Y equals k times x. And so that just shows you that's a direct proportion. That's saying that when x gets bigger, y is going to get bigger. So this is what we want, inverse proportion. So we want to write an equation expressing f as a function of r. So the magnitude F, which is the force exerted by the Earth on an object, is inversely proportional to the square of the distance r. So that's going to be times r squared. So x times y equals some constant k. Then it says write an equation expressing f as a function of r. So I'm going to make this so I can explicitly take the derivative. So I'm going to just divide both sides by r squared. Okay, and so that gives me the function f of r equals k divided by r squared, which I'll write as k r to the negative 2. So that is our function. This k is some constant. We're not told that in this problem. Write an equation expressing the derivative of force with respect to the radius as a function of r. So the derivative of this function would be negative 2 times some constant k r to the negative 3, which ends up being negative 2k divided by r cubed. Okay, so what is the physical meaning of the derivative of the force exerted by the Earth with respect to the radius and or the distance that body is from the center of Earth? Well, it turns out that this is Newton's law of universal gravitation. And Newton's law of universal gravitation is this: G, which is the gravitational constant that Earth has, times the mass of the Earth times the mass of the object divided by r squared. That's Newton's law of universal gravitation. So that k is actually all of this stuff right there. And so the physical meaning, it's a derivative, it's a rate of change. So what this is saying is it's an inverse proportion, so we can see that as the radius gets bigger, this denominator gets bigger, the force exerted is decreasing at a rate of that, and that would be y units per x unit, but we aren't given much information. Okay, this is the last example we're going to do before we go back to rectilinear motion. All right, this one says a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area with the circle or of the circle is increasing after 1 second, 3 seconds, 5 seconds. What can you conclude? When I first read this, it felt like some problems called from the section called related rates, which we're going to do after test 2. But you don't really need to know about related rates to do this one. So we do want to start understanding drawing pictures and understanding what's happening by looking at what we're told. So here's the stone, and it's dropped into a lake, and it causes circular ripples, and the ripples are getting bigger. So the ripple is traveling at a speed of 60 centimeters per second. So this we can call R for the radius of the circle. And what we're given here, you can tell by the units, well, it's a speed, so it's a rate of change. You can tell by the units, this is dr with respect to time, because that's seconds. Okay, so we have to demystify that. All right, then it says find the rate at which the area of the circle. So when we do related rates, and including this, we're going to have to think about certain formulas. We know the area of a circle formula is pi r squared, but we don't want that. We want to know the rate at which the area of the circle is increasing. And this is where it seems like related rates after time, with respect to time. But we are not there yet. So what we're going to do is we're going to think of the formula for the area of the circle, which would be A equals pi r squared. Okay? And then we're going to take the derivative of this area with respect to r. Okay? So that would be dA over dr equals 2 pi r. All right, so now if we're given r, the radius, we'll be able to find the rate in which this area is increasing. Right? So what's difficult a little bit is that you don't know what r is, right? But you can figure it out because you know the rate at which the radius is changing with respect to time. So that's what's tricky about it. So what we can do is we can say, well, let's think about what happens after 1 second, right? If we know that this radius is traveling, or these ripples are traveling at a rate of 60 centimeters per second, then how far has it gone out after 1 second? Well, that's a rate, 60 centimeters per second. This is a time, so we can just use D equals RT, and then the seconds cancel. And so we can see that after 1 second, the distance is 60 centimeters. Okay, so now that's R, and now I can plug it into this. So if we plug this radius into our derivative of area with respect to the radius, we get 2 pi times 60, which is 120 pi. All right, let's look at the units here. So this is a derivative of area, and the distance is centimeters, so that would be centimeters squared, and this is radius, which is in centimeters. So the units are 120 pi centimeters squared per centimeter. So we can see that as the radius increases, the area is going to increase at a rate of 120 pi centimeters squared per centimeter. All right, we can do the second one. So what happens after 3 seconds? Well, we can figure out by this rate that after 3 seconds, 60 centimeters per second times 3 seconds, using D equals RT, is 180 centimeters. Okay, so that means that the derivative of A with respect to R, which is 2 pi times R, so that would be 360 pi centimeters squared per centimeter. All right, and we can do the third one at 5 seconds. That means we've traveled 60 times 5, 300 centimeters, or the ripple has. And so dA with respect to R is 2 pi times 300, which is 600 pi centimeters squared per centimeter. And then what can we conclude? Well, you can see that as time goes by, as time increases, the radius increases. As time goes up, the radius goes up, and the area goes up. So that's our conclusion on that one. But these, we just need to start learning how to track units out. Okay, we really need one more straight line motion problem or rectilinear motion problem. So here is one from the ebook. This is number 1 in section 3.7. And I just took the relevant pieces out, and we're going to go through all of these. So you may want to pause the video and write this down, whatever you want to do, but this is really, really important. So, okay, a particle moves according to a law of motion, straight line motion, and it's f of t equals t cubed minus 9t squared plus 24t, and t is in seconds, and f of t is in feet. So this is a position function. And we want to do the following things. We want to find the velocity at time t. We want to find when the particle is at rest. We want to know when is the particle moving to the right or to the left. We want to find the total distance traveled during the first 6 seconds. Find the acceleration at time t. And when is the particle speeding up and slowing down. So I wanted to do one more of these because the first one I did with you, the way the question's asked, we found the total distance first. But really, it's easier if we find where the particle is at rest. Because when we're doing this graph, we're going to have some turning around. It's going to go to the right, it's going to go to the left, it's going to go to the right. And so we can tell where that happens by finding the velocity and where it's at rest. That's where it's turning around. So take a note of that. All right, so the position function, the first derivative of the position function will give you the velocity function. Okay, so the first derivative would be 3t squared minus 18t plus 24. So that's A. And then immediately you're going to want to find out when the particle is at rest. So the particle is going to be at rest when the velocity equals 0. Okay, so 3t squared minus 18t plus 24 equals 0. We don't need our calculator to solve that. We can divide out by 3. That gives you t squared minus 6t plus 8 equals 0. That factors into t minus 4. T minus 2 equals 0. So t equals 4 seconds and t equals 2 seconds. So now we know that not only do we know when the particle is at rest, we know that that's where we're going to be turning directions. So that's why that's helpful to do first. All right. C, it says when is the particle moving to the right or to the left? Okay, so what's going on there is we are going to be solving these two inequalities. 3t squared minus 18t plus 24 is greater than 0. That's when it's moving to the right, when the velocity is positive. And 3t squared minus 18t plus 24 is less than 0. That's when it's moving to the left. So I'm not going to always write that down because we already did the first step. To solve a quadratic inequality, you find the zeros first, and then you draw a number line. Okay, so the number line is going to have 0 because time can't be negative. Okay, so this number line is t, and then you've got 2 and you've got 4. And so then you just analyze these two inequalities. Well, we've already factored it, so t minus 4 times t minus 2 is greater than 0, or t minus 4 times t minus 2 is less than 0. So again, I'm not going to write all this out all the time, and you shouldn't either, but I realize that this might be something you forgot how to do in 171. So basically, what you do is you find the zeros, you put them on the graph, and then you just check what is happening, and you can just pick one number in each of these intervals. So I'm going to pick 1, and I'm going to put 1 in here. Okay, and when I put 1 in here, I get 1 minus 4, which is a negative, and then 1 minus 2, which is a negative, and a negative times a negative is a positive. This is what I call sign analysis. And then I'm going to pick 3, and I'm going to put it in here. And when I get 3, I get 3 take away 4, that's a negative 1, and 3 take away 2, that's a positive, and a negative times a positive is a negative. So see, that's why we don't really need to write all this stuff down. All we're going to do is find the zeros and then pick numbers and plug it in to this piece right here. All right, so if we finish up, we pick a number like 5, we put it in here. 5 take away 4 is positive, times 5 take away 2, that's a positive. So I don't care that it's 5 times 1 times 3. I just care about the positive and the negative, and then I use multiplication rule. So positive times a positive is a positive. And so now I know exactly where it's moving to the right and moving to the left. Okay, so this particle is moving to the right when this is positive. So that's between 0 and 2 seconds and after 4 seconds. And it's moving to the left when this is negative. So it's moving to the left between 2 and 4 seconds. All right, so that's C. And then now D, it's going to take a little time. I want to do this now with this added information. It gets a little bit easier. And there's a certain way to do it. Find the total distance traveled during the first 6 seconds. So like before, I'm going to create a table of values. All right, so I know we want to know what's going on the total distance, the first 6 seconds. Okay, so the easiest way to do this again is to put this in your calculator. So you can pause the video and put the function, the position function into the calculator. I've already done it, so you want to make sure you pause the video. But you hit table, and then you hit 2 for edit, and then this is your X button, and then that button for the cube, put the 3, and then make sure you go back down, -9, and then this X squared plus 24X. So now I have my position function in there, and I want to start at 0 and count by ones and go to calc. And so I can copy these values down. At 0 seconds, it's 0 feet, and then 16 feet, and then 20, and 18, 16, 20, and 36. Now, so before I kind of did this intuitively, and there were in the first example there were a lot of negatives in here, and so these are all positive, but you can go back and do the first example this way, because see, now it's really better to have this information. See, now we know that on the interval from 0 to 2 seconds, we are moving right. And on the interval from 2 to 4 seconds, we're moving left. And on the interval from 4 to 6 seconds, we're moving to the right. And so we know that there's a change of direction at 2 and 4. And so that helps with this graph. Okay, now, how do you graph rectilinear motion? Now, it's hard because I already did a number line like that, and this was T. But when you're graphing this, it's not, this number line isn't T. This number line is going to be F of T. Okay, so we're going out to 36. So we'll have to make a lot of little marks here. So I'm going to just do this. That's 16. That's 20. And that's 36. Okay, so we can see those key numbers there. And there's a few other key numbers in here. So the way that you graph this, remember this is f of t. So we put a little dot and we put the time, we kind of label each dot with t, the time. So at t equals 0, we're at 0 feet. And then at 1 second, we're at 16 feet. Okay, and then at 20 seconds, but see, I already know I'm going to turn direction, so that's going to make my graph a little prettier. So I'm going to make this curve and turn around like that. So at t equals 2 seconds, I can see I'm changing direction. This is where I'm at rest. And then 3, we're going to go back to 18, which is right here. So t equals 3 right here. And then again, because I did that velocity analysis first, now I know I'm changing directions at 4, t equals 4, and it's 16, so I can make a little prettier picture and make that curve t equals 4 like that. And then at t equals 5, I'm going to go to 20. So that's t equals 5 right there. And then at t equals 6, I'm going to go up to 36. So that is what my straight line motion graph would look like for this one. And see, you really need this information because, you know, it could change directions at a decimal, at 2.5. And so the first example, I sort of just kind of did it intuitively, but this is a better way of graphing. All right, now, also, how do you find the total distance? Well, before I just kind of did it intuitively, but now what we can do is use these intervals of change to calculate. So as long as you're going in the same direction, you can just group those together. So from 0 to 2 seconds, and we're going to use absolute value, I went from 0 feet all the way up to 20 feet. So I just do this y2 minus that y1, okay, because we're trying to find the change in the distance, and these are y's, okay? So that's 20 feet. Then you can take that second interval where we're not moving to the right, we're moving to the left. So this time our y2 would be 16 minus 20, and see how that would be a negative? That's why you use absolute value. So from 2 seconds to 4 seconds, I go from 16 feet, I go from 20 feet backwards to 16 feet. So that would be 4 feet. Okay, and then from the interval from 4 to 6, I'm going back right again. So that would be this 36 take away 16. You can see that. So that would be 20 feet. So it gets a little more clear this time, I hope. So we want to use absolute value, and we want to use the intervals that we found when we did the velocity. And that's going to make this a little bit more, it's a less intuitive, and you can do it this way every time. You find the change in the direction, and you take the second number minus the first number, absolute value, change in direction, second number minus the first number, absolute value, change in direction, second number minus first number, absolute value. Then you add them up and get 44 feet. So that's exactly how you do these problems for greatest success. All right, let's move on to the acceleration at time t. So remember, acceleration is the derivative of the velocity, which is right here. Don't use where you divided by 3. So the derivative of 3t squared minus 18t plus 24 is 6t minus 18. All right, and then we want to know where the particle is speeding up and slowing down. So we did that at the beginning of this video. And so again, what we want to do first is find the critical point. Where is it equal to 0? And that's at t equals 3 seconds. All right, and we learned that speeding up is acceleration, and that's when the velocity and the acceleration signs are different, are the same, and slowing down is deceleration, and that's where the velocity and acceleration are different. So we're going to go back to what we did here. I'm going to just copy that down, but then we're going to add the acceleration information. So now we're back to this line meaning t, and our key points are 0 and 2, and 4 from the velocity, but now we're adding 3. Okay, so the velocity, we know, had a plus, a minus, and a plus. Okay, now the acceleration, again, what we're doing is we're just seeing we're going to pick a number and see when is 16 minus 18 greater than 0 and when is 16 minus 18 less than 0. So I don't normally write that down, but that's what we're doing. So I'm just going to plug 1, do a 1. And so when I put 1 in anywhere of these, I just analyze it. 6 times 1 is 6, take away 18. That's a negative value. All right. And then I'm going to pick a number after 3, because my critical point for the acceleration is 3. So let's pick 5. And so, okay, hold on. Let's add that. So I got to add that. So that's a minus. That's a minus. Okay. Anything to the left of 3 is a minus. All right. And then let's pick something to the right of 3. We could pick 4. 6 times 4 is 24. Take away 18. That's a positive. So anything to the right of 3 is a positive. Okay. So you may want to fix this so you can have all of your choices. So I'm just splitting this interval between 2 and 4 for the velocity. Instead of one big negative, I'm putting 2 negatives. So now you can see where the sign changes are occurring perfectly. All right. So it is speeding up when the signs are the same. And doesn't matter whether they're plus, plus, or minus, minus. It's speeding up from 2 to 3 seconds, and it's speeding up after 4 seconds. And then it's slowing down or decelerating when the signs are different from 0 to 2 seconds. The signs are different. Where else are they different? And then 3 to 4. It's slowing down. Okay, so I hope that example helps. I will post a picture of this for you because I want you to be really good at rectilinear motion.